Hi, am I audible now?
Yes, we can hear you.
Yeah. So, hello everyone. This is Aditi from IIT Kanpur, India. What I'm going to present today is um, is an experiment, a part of my thesis work, and the title of the presentation is Attentional Bias for Cell-Based Investigation using Diffusion Modeling. There's a huge literature demonstrating that our cognition is biased toward the self, and this self bias has been originally called the self-reference effect. Trait adjectives paradigm and ownership task have been used to measure self-reference effects in the domain of memory. It is found that our memory for the objects or adjectives related to us is better than for the ones related to others. This self-reference effect for memory has also been observed in adults as well as children. Shape label matching tasks have been used to test the effect of newly established self-association with arbitrary shape on perception. Results have shown an advantage in terms of reaction time and accuracy for self-associated pairs, despite contrast reduction, depicting the effect of self-reference on the low-level perceptual processing. A similar advantage has been observed by some studies when self-face is taken as a stimulus. Perceptual judgment for orientation, that is when people are asked to report whether head is facing leftward or rightward. The judgment is faster for our own face than for the other faces. Memory-based familiarity judgment tasks, they have also supported self-face advantage over other face. In one of our previous studies also, prior entry effect for self-face has been observed for both direct temporal order judgment as well as orthogonal emotion identification task. The mechanisms behind the self-face advantage may include increased emotional arousal, implicit positive attitude towards the self, dual encoding, that is configural and featural processing of self-face, multisensory information integration, integrative self-hypothesis, and the dopamine reward pathway. Another mechanism proposed in the literature is the automatic capture of attention by self-face. However, there is another set of studies which have shown that self-faces can influence processing due to problems in disengagement of attention from the self-face when it is attended to. One way to tease apart the effect related to attentional capture versus disengagement is to use a dot proof task. So in this task, a prominent stimulus or the cue and a neutral stimulus are presented at the same time in different spatial locations. For example, one to the left and one to the right of the central fixation point. And it is followed by the presentation of a target at cued or non-cued locations. Faster responses typically observed in the cue congruent trials are interpreted as evidence of an attentional bias to the location of the prominent stimulus. So to investigate whether the deployment of attentional bias occurs for self-face, we used a dot proof task cued by face pairs, self-friend, self-unfamiliar, and friend-unfamiliar to understand how performance on this task is mediated by the processing of self-faces. It should be highlighted that in each pair, one cue face is the preferred face and the other one is non-preferred. So for example, in self, friend, and self unfamiliar, self was the preferred face, and in friend unfamiliar, friend was the preferred face. To understand what components of attention processing are affected by the self-face cues, faces were presented as cues at left and right visual angles before the target, which in our case was an asterisk. And the participants had to respond to the location of the target, whether left or right, by pressing Z or M. Cue presentation time was manipulated as 50 and 150 milliseconds as it reflects different stages of processing. The interaction between Q by the preferred phase and Q time, that is 2/2 repeated measures ANOVA, was analyzed for all the 3 phase pairs. We expected that if automatic attentional processing is the primary mechanism via which cell phase processing advantage occurs, one would expect cell phase to grab attention, resulting in cell phase influencing the processing of the probe congruent to it. We first did the basic reaction time analysis. So for the self-friend pair, that is when self is the preferred Q and is paired with the Q friend, the main effect of Q time was found significant. Tukey's post-hoc analysis indicated that the reaction time was faster for 150 millisecond Q time as compared to that of the 50 milliseconds. However, in this case, no differential attentional bias is observed towards the self phase. For the self and familiar pair, and that is when self the preferred Q was paired with the unfamiliar phase Q, the main effect of queuing was found significant, and post-hoc analysis indicated that the reaction time was faster when cell phase and target were congruent as compared to when they were incongruent, which supports the basic hypothesis of dot probe paradigm. So we can say that cell phase can bias attention when presented against an unfamiliar phase. For friend unfamiliar pair, the interaction effect of Q time and Q was found significant. We found that for long Q time, reaction time for the congruent condition was significantly faster than the incongruent condition. We also found a significant difference between RTs for 50 millisecond and 150 millisecond Q time for congruent condition. So all in all, on the basis of reaction time results, we can conclude that both familiar as well as cell phase can bias attention when presented against an unfamiliar phase. The difference is that for cell phase, this bias occurs early as well as for late duration. However, for a friend phase, the bias is seen only for the longer Q durations. Lastly, when a cell phase is paired with a familiar phase, no differential attentional bias is observed. Similar accuracy analysis was conducted for the 3 phase pairs. None of the main effects or interaction effects were significant for accuracy. So later, to understand the underlying mechanisms of parameters determining the behavioral results in the reaction time analysis, we conducted the drift diffusion modeling for all phase pairs in the next section. The drift diffusion model, it assumes that during a 2 alternative force choice task, example in this case, responding to the location of the probe, whether left or right, noisy information is continuously sampled until sufficient evidence is acquired to initiate a response for one of the choices. The parameter drift rate, it estimates the speed of the information gathering. That is, larger drift rate is meant to have faster information uptake or faster reaction times. Another parameter of interest, the starting point Z, defines the position between the decision thresholds at which evidence accumulation begins. So if Z is not centered between the thresholds, that is, if it is 0, it's not 0.5, this denotes a prior bias in favor of the response that is closer to the starting point. That is, less evidence is required to reach that threshold. The other 2 parameters, that is threshold A and non-decision time T, are not of our interest in this study for the time being, so I'm not elaborating them here. We used hierarchical drift diffusion modeling, which is used for the hierarchical Bayesian estimation of drift diffusion model parameters. So models were response coded such that the upper threshold corresponded to the response congruent to the preferred phase. For example, self was the preferred phase in self familiar pair and self-unfamiliar pair, and friend's face was the preferred face in friend unfamiliar pair, and the lower threshold to the non-preferred faces. To identify the mechanism by which self-face biases information processing, we calculate deviance information criterion values for models with V, that is the dynamic bias model, Z, that is the prior bias model, and V and Z both, that is the multi-stage model, when being allowed to vary as a function of Q congruency and Q time. We have used only these two parameters related to models because in this framework, in drift diffusion model, a bias can arise in two ways: by either shifting the starting point of accumulation towards one of the bounds, or by changing the rate at which evidence for one versus the other choice alternative is accumulated. So that is why these two parameters we are going to explore. The DIC value for a model reflects the overall fit to the data at the participant and the group levels. The model with the least DIC is considered the best for defining the performance. So by comparing the DIC values of Q time cross Q model with the null model, for all the phase pairs, we found that the value for all models is smaller as compared to the respective null models. And on the basis of this table, we see that the drift rate is determining the performance advantage for self when it is paired against an unfamiliar face, while for the other two cases, prior bias is playing the role. As mentioned earlier, for self-unfamiliar phase pair, we observed the lowest DIC values for the dynamic bias model, where the parameter V was allowed to vary freely, while other parameters were kept fixed, indicating that presentation of self face against an unfamiliar face, it increases sampling rate for subsequent targets, especially for higher Q time at the congruent position. For self-familiar and friend unfamiliar face pairs, we observe the lowest DIC value for the prior bias model, where parameter Z was allowed to vary freely with Q time with Q time cross Q model, while other parameters were kept fixed. The third bold row indicates that the Bayesian p-value supports that the parameter Z is greater for the preferred phase as compared to the non-preferred phase. Results suggest that reaction time benefits that we see earlier for the friend phase compared to an unfamiliar phase are due to an increase in bias towards the friend phase for greater Q time. Similarly, we see a greater starting point bias for self face also against when it is presented against a friend face. The overall results indicate that although self face and friend face, they both show a queuing advantage over unfamiliar faces, but the advantage for a friend's face results from a prior bias, and the advantage to a self face results in an increased sampling rate for subsequent stimuli. When self face and friend face are compared with each other, we still observe some processing advantage for self face. All in all, we can say that the results support that presentation of self face results in an attentional bias towards itself. A similar advantage is also seen for familiar faces. However, it might be wrong to reduce the self-face processing related interactions with attention to familiarity, because our results show that the kind of biases that familiarity creates versus the kind of biases that self-referentiality creates might be different. While familiarity results in a bias for initial selection towards the familiar face, processing a self face might result in a subsequent increase in the rate at which information is sampled from the region in which self face was processed. Coming to the limitation, despite these major findings, results are not completely conclusive about other aspects of self-phase processing. For example, we did not find an increased sampling for self-phase when it was compared with a friend's phase directly. Similarly, we did not find any self-phase advantage in the processing of incongruent trials. So yeah, that is on my part. So yeah, thank you.